Okay, so welcome back to this week 3 of this course, and we're gonna talk this week more about the random walks and the connection to group theory in a very deep level. So we want to really understand now how the group structure will be present in the study of the random walk. So this is like where really there will be some difference to a normal type of a random walk due to having a general probability space, but here we actually take an advantage of the group structure in here. So that's why I want to introduce this notion of convolution of the random walk. So convolution is a way to transfer this information about the group into the language of the probability theory. So the convolution basically is a notion where it allows to talk about the evolution in time. So when we start to like several times apply, let's say, a random procedure, we want to be able to like get some information about what happens when we like evolve the random walk according to some time. So what we can do here is the following situation. So let's start from this like basic example that we have already seen. So let's start from this basic random walk that this is the Z4 over here, and then we have this idea that okay, this is the point 0, 1, 2, and 3, and then we start to, let's say, move from here. That let's say we start our walk here, like if we had this talk about broccoli, we have this like position that we have starting from this position 0, and then we move with let's say probability half to the right, and then probability half to the left. So that was kind of the basic random walk we started to consider, that we either move from right to left depending on the of what the outcome of the throw of a coin basically would have been. And then after this, the idea that okay, let's say if we reach here, then with probability half, we go back here and to the right, and then again with probability half, we go back on the other side. And then the same way with probability half here, we would go back here and then probability half on this direction. So basically what we are doing here is that we are starting initially, let's say at this point, and we take a random choice according to this probability distribution mu t, which is given by half of the Dirac mass at 0 plus half of the Dirac mass at sorry, not at 0, at 1, and then at the point -1. This was like going into right, sorry, this mu, use this distribution mu, which is the like a sum of these distributions. Remember that this just means that I'm just using this kind of convention, that this means basically that this is a half if t is equal to 1 or -1, and it's 0 otherwise. That being Z4 in this case. And when we start from the position 0, then we are moving to the right. So basically we made a random choice according to this distribution mu. But now when we have, let's say, reached a point, let's say we have reached the point here, for example, and now we could make another random choice with probability half or probability -1 to the left and the right, then we can apply this again, basically. So there is this kind of conditioning that we've reached to this state half, this state 1 in this position, this red area that we have written here, and then we again make a random choice based on the same distribution mu, whether we go right, so whether we add 1 plus 1, or whether we move to the left, so we subtract 1 from the point 1. And the weights will change. So in some sense, like basically what we have reached, that it's if after 2 steps, where if you start from 0, we will end up that it kind of spreads into these possible states that the random walk has possible reach. It could have reached from the right to the point 2 and from the left from the point 2. So there are several places that it could have reached to in this situation. So there will basically be a new distribution coming out of this process that you get by taking basically 2 steps, and that's called the convolution. So that's the convolution of like adding this twice. So we define this now formally. So I'll show you how this links into this. So this is called convolution. And convolution is defined for any functions you get to see. So let f and g be functions from zp to c, and the convolution of f and g is this function f star g from zp into c, defined by f star g at the point t is just defined to be the summation of s in zp. So you're summing over all the s's, and you take f t and you subtract s, and then you take g of s. So this is at the points t in zp. So remember that this notation was just the t minus s modulo p. That's the notation that we use. So that's the convolution of the 2 functions. And if you think about the probability distribution, what we had, so let's go back to this example that we consider here. And we want to basically see that why this convolution describes the random walk. So assume, let's take an example. Let's assume that f equals g is equal to this mu, which is the half of Dirac 1 plus half of Dirac minus 1. So let's take this example and let's compute the convolution. So mu star mu at the point t, by definition, so if you open up the definition, is s in zp. Actually in this case I'm using, we are using the z4, p is equal to 4, what I'm using here. And then you have the mu at t minus s, and then mu t. And once you start opening this up, if you look at the definition, this actually means that this is just the weights that this is. Remember that this is 0 if t is not equal to 1 or t not equal to minus 1. Then basically the only places where it is equal to 1 or minus 1 is when it's minus 1 or plus 1. And then here, if you look at the definition, this is equal to a half if t is equal to 1 or t is equal to minus 1. So that's why you have that this is actually equal to half of mu, and then take the point t that we wanted to consider. Sorry, this should be s here. I just realized. Yeah. S. So that's why you get basically the point t, and then you have minus, well, the first point is, let's say, minus 1, and then you have the a half mu t minus 1, which then, if you translate this into the kind of language you have, so half of mu t minus 1 plus half mu t plus 1. That's the convolution that you get, and you can actually compute these numbers. If you open this up with the definition, you get that this is, because now this point, what we have here, is actually taking the Dirac mass at the point half. So this is actually, if you open this whole thing up, mu at this point is a half. So this is actually a half of half at Dirac point at point 2 at t. Because remember that this quantity mu t minus 1 is 1 precisely when t minus 1 is equal to 1. So just to remind you that mu t minus 1 is equal to, so this is a half if t minus 1 is equal to 1 or minus 1, and it's 0 otherwise. So if you have this condition here, minus 1 or plus 1, then that condition is basically the same as if you add it to the other side. So if t is equal to 2 or t is equal to 0. So you can get the other guess 0. So that's why you have this is equal to half at the point this one, and then you have plus half at the point Dirac at 0 of t. That's for the first one, and then the second one is plus half of the, I have to like same way, so this is at Dirac at 0 of t plus half at Dirac of minus 2 of t. That's the, I'm just using this again for this one over here. I mean, actually use a color so you see the how does it look like. So this one is over here. That's using the definition of mu, and then we have the green one here. This is the definition of the green one. Okay. So if you now open this up, you just get this is equal to, this cancel out, and I think you get 1/4 Dirac 2 of t plus half Dirac 0 of t and plus 1/4 Dirac minus 2 of t. So that's now the convolution. So if you see the whole thing now here is that mu star mu at t is equal to this number. So basically this proves that the convolution is equal to this distribution, Dirac at 2 plus half Dirac at 0 plus 1/4 Dirac at minus 2. So that's the definition of this mu star mu. And now if you look at the intuition that we used in the same way, so initially, like if you look at this this probability, so this is saying that after 2 steps the only possibilities where you could be is at either 0 minus 2 or at 2. So if you look at the group, let's look at the what it looked like. So for example here, this is 0, this is 1, this is 2, this is 3. So what is the inverse of 2? So if the one that adds into 2, so it's actually the minus 2 is equal to 2. That's the inverse of 2. So basically what the distribution has to look like after 2 steps is that it's just this actually equals to the same point. If you actually look at the inverse of 2, this becomes a half of Dirac at 2 and then plus half of Dirac at 0 as 2 is equal to minus 2. That's the 2 modulo 4. That's what we have. So you have basically a half weight here and then you have a half weight here. So that's the convolution mu star mu. And you started from something that was, let's write it here, this is what you started from, this is the mu. So you put the weight on 1 and the minus 1, and you get this kind of distribution. So this basically shows that when you apply the random walk twice, and if you, let's say, started from 0, that you started from this point at 0, then the only ways where you can move on from here is basically to the right or to the left. So that's the first step of the mu. So when you apply the mu once, you're basically the only place where you can move is with these 2 points mu. And then when you are at this point, the next place, let's say, then the only places where you could move is with probability half to the left or the probability half to the right again. And the same way from here. So that's why in the convolution, the only places where you could reach at the second stage would be these 2 points at the here. So this mu star mu where you could reach at this stage. So it's basically telling you that it makes sense what we have here, what we computed with this formula. We get exactly the same kind of intuition that if you, the only place, there's probability 0 that you could reach the state 1 or state 3 after 2 steps, because when you in the first step you already reached to the point 1 or 3, so in the second stage you can only reach to the other points.